Welcome to the second chapter of mobile communications. In this chapter, I will focus on wireless transmission. Remember, this is a course mainly for computer scientists, so I will only briefly touch the major issues of wireless transmissions. I will talk about frequency, signal characteristics, antennas, MIMO, multiplexing, how you can mitigate certain interferences. I will talk about modulation and cellular systems in general. So let's start first of all with frequencies. Frequencies we use for communications. I mean, you know many different frequencies in our everyday life. You switch on the radio, the television, you use your computer, you use wireless LAN. Well, even the sun shines, and these are all electromagnetic waves. So if we talk about visible light, this is only a small portion of the spectrum of electromagnetic waves. So visible light around 300 whatever something terahertz, well then we rather talk about the wavelength, so something like 850 nanometers, and oh, what a lovely flower with some whatever leaves in whatever nanometer or blossoms. Well, usually we use the term color, like red and blue and green and yellow, but this is nothing but wavelengths or different frequencies. So if you're confused, it's very simple to go from frequency to wavelength. Basically, the wavelength is the speed of light divided by the frequency. So that's all. So speed of light, we simply assume this is roughly 3 times 10 to 8 meters per second. That's the speed of light. We all know from physics this is speed of light in vacuum. Well, in real life we have the air, we have whatever glass, walls, wood, people in between the sender and the receiver. This all slows down the electromagnetic waves. But okay, for now let's assume this is the speed of light, 300,000 kilometers per second. If you look at the spectrum, you will see very low frequencies, well used maybe by submarines. Not interested here. The frequencies we usually use, they're around, let's say for wireless transmission technologies, they're around 450 megahertz. They're interesting systems up to something like 5 gigahertz. There even 60 gigahertz systems. But think of, for example, wireless LANs. They're somewhere here. So wireless LANs or mobile phone systems, LTE, etc. They're all in here. Why? Well, we'll see in a minute. There are certain frequencies you can easily use in our environment. They can easily penetrate buildings, for example, down to the basement. Or, well, there's also a problem. You have to be able to build such a system. We'll see the lower the frequency, the larger the antennas. So that's a problem. On the other hand, we cannot simply use light. Light, okay, that's nice. But a simple wall would block the light. So there are certain frequencies we can use. Okay. The frequencies we use here are usually in the range of the so-called ultra-high frequency, super high frequency, UHF, SHF. So, just some examples. We use these VHF, UHF frequencies for usually traditional analog radio, even digital radio. So it's very reliable. It's a simple system. You can have small antennas on the roof of the car, for example. For even higher frequencies, well, we can use electromagnetic waves, for example, for directed radio links, so microwave connections from one antenna to the other antenna, huge antenna masts or poles, and then you can more or less direct a wave from one antenna to the other. And this is what I just drawn here. It's the main coil of where the signal energy goes into, and then there's some minor calls we'll see as well in a minute. So directed microwave connections. So 40, 50 meters high antennas with these round dishes. With higher frequencies, you can even form a nice beam. Think in the ideal case of a laser beam, for example. It's way more difficult for lower frequencies. And for higher frequencies, we can use a much larger bandwidth. And if you remember, for example, from computer networks, bandwidth, oh yes, there was something like Shannon and Nyquist, all these theorems. Then if you rethink of the formula there, it says, okay, the data rate is directly proportional to the bandwidth I can use. So that means the higher the bandwidth is, the higher the data rate can be. So bandwidth is important. I will come back to this as well. So we can think of many different systems, but there are also some limitations. So for example, for wireless LANs, usually we use frequencies like 2.4, something around 5 gigahertz. If we now look at the 2.4 gigahertz, well, and then if you look up the specs of your microwave oven, you will see, oh, the microwave oven also operates at 2.4 gigahertz. Why? Because there we can use something that's called dielectric heating. So we heat up the water, for example, in our spaghetti, so we can eat the spaghetti, warm spaghetti, instead of cold spaghetti using the microwave oven. So, but what does this mean for our wireless LANs? Well, we have something, for example, like weather-depending fading. So if it rains, then our wireless LAN or any other cellular system simply heats up the rain. So we will lose some of the signal energy by heating the rain. So this will not be hot rain, but we will heat it up a little bit. So we will lose some of the energy. The energy is absorbed in the rain. It heats up the raindrops a bit, for example. We will lose the energy. That means the signal is weaker on the receiver. So it can happen if there's heavy rainfall, for example in tropical regions, that the cellular system breaks down if we do not have enough antennas. So similar effect you will see if there's heavy snowfall in winter, for example, then the satellite transmissions will have at least strong interference or even break down. So you have to consider this. So even your wireless LAN at home heats up water. Well, heats up whatever, heats up your body, for example. Well, that's not really a problem because the output power of your wireless LAN, we are talking here about something like 1 watt or something like 100 milliwatts. That's something for your wireless LAN typically. For your microwave oven, we are talking about 800 watts. So, and usually the waves are contained inside the microwave oven. So please do not open the microwave oven and switch it on. Stupid idea. Okay, so we now know a little bit about frequencies. But the problem with frequencies compared to wires is that as soon as you emit an electromagnetic wave, it travels from the sender into the space around the antenna, and then there might be interference if, for example, your neighbor also wants to transmit something using the same frequencies. Or think of classical analog radio stations. If there's a radio station here transmitting on a frequency you want to use for your wireless LAN, that's a stupid idea. So many years ago, people already came together and said we somehow have to coordinate this. And just to give you some examples, so there's today the ITUR is responsible for the management of the frequencies, for auctions, for new frequencies, managing frequency bands. Within so-called World Radio Conferences, many people come together and then they coordinate the frequency use, usually in certain regions. Why certain regions? Well, for example, Japan is an island, so if you use a certain frequency in Japan, well, there's no real big interference, for example, in Europe or the US. Still, there are some things to consider. for example, if you want to use the same device in all different countries. Now let's have a closer look to wireless LANs. Here you see, oh, nice. That's just an example. At the 2.4 gigahertz range, so here it's shown in megahertz, 2.4 gigahertz range, well, there is some nice overlap. There are some differences. So we all more or less start at 2412 megahertz, and then we go up to, in Europe, to 2472, in the US to 2462, oh, in Japan even a bit more, just as an example. What does it mean? Well, at least there's a big overlap. That means you can use your Wi-Fi adapter in all these regions, and that's quite important, because otherwise you could not use your Wi-Fi adapter in your laptop or tablet if you travel from Europe to Japan. What a stupid idea. Still, there are some rules to obey. For example, there are more so-called channels available in Europe compared to the US. For example, we will see later on when I discuss wireless LANs what the channels are, etc. But you see right now there's a bit more of the spectrum available in Europe compared to the US. Many reasons for this. Whoa, well, how is this solved, for example, for cellular networks? You see many different frequencies here. For example, let's focus on Europe and the US. For the GSM system, many frequencies around 900 megahertz, around 1800 megahertz. So this is, when I mention these frequencies, these are, well, the frequencies, around these frequencies we have a part of the spectrum. So around 900. And you also see always a pair of frequencies. I will come back to this. This is, which I will discuss later, for the downlink and the uplink. So there are uplink frequencies and downlink frequencies in the so-called paired bands. I will come back to this. But here it's important to see, oh, there are different frequencies for systems in Europe and the US, for example. And on the same frequencies, we might have different systems. Well, it's quite obvious, for example, that GSM, the classical second generation mobile phone system, operates in Europe around 900 and 1800 megahertz, and in the US, usually it started around 1900 and then around 850. So we have something like, just for GSM, something like 1900 and 850 in the US, and we have something like 900 and 1800 in Europe. What does it mean? In this case, just for the example, GSM, in this case, we cannot use the same frequencies for the same system in US and in Europe. And that means for the radio transceiver, the hardware in your mobile phone, it has to adapt. So it has to tune into the right frequencies. That means as soon as you, for example, land in Europe, you're coming from the US, your mobile phone system will discover, oh, now this is Europe, so I have to go to different frequencies, listen to different frequencies, and then this cellular phone system will tell the mobile phone, please use this and that frequencies. And this is why today, for example, for GSM, we have so-called quad-band receivers, because they can operate on four different bands. So quad-band receivers. So it starts with single-band, then dual-band transceivers, tri-band, and now quad-band transceivers, for example. That's the first thing we learn. So, same system, GSM in this example, on 4 different frequencies. Reasons for that is availability of the frequencies, different operators, different characteristics. Usually the problem is you cannot have a clean slate approach. That means, oh, there's no one using any cellular system, and now I can deploy my system. No. Usually you have older systems operating there already, and this means, well, I cannot use these frequencies. For example, in the US, 900 megahertz is already occupied by different systems. You cannot use it for cellular phone systems. That's the first thing we learn. Then if we compare, in this example, Europe with the US, we learn a second thing. If you look at Europe, you see GSM on these and these bands, UMTS, third generation system, on these bands, LTE on these bands. So in Europe, usually the different systems do not overlap in frequencies, because in Europe, usually the authorities say, for this frequency band, so part of the spectrum, for this band, we allow this or that system. So if you have a new frequency band, you say, okay, this is now for LTE. And then different operators can use the LTE technology on this band. This means there's no interference between different systems on the same frequencies, but you need a certain authority that says, okay, this is the technology to use on this band. The US has a different approach. In the US, usually the authority says, okay, we set certain rules and guidelines for the technology, for example, maximum output power, to minimize interference between different systems, and then let the market decide. So the market has to decide which is the more successful system on the 850 megahertz band, for example. Could be GSM or a classic LAMP system or whatever, CDMA system. The same for 1900. And there are also LTE systems, etc., etc. So this table gives you only some examples. So there are two different approaches. The European approach is rather let the authorities decide which system on which frequencies. There's a lot of discussion, including industry, etc., before the decision is made. The US approach is rather we give certain guidelines and then let the market decide. So and then we have cellular networks on different frequencies. We have cordless phones on different frequencies, analog and digital systems, wireless LANs, and then other RF systems, so radio frequency systems. For example, whatever remote control cars, garage door openers, whatever there is, door openers, things like this. So, or toys, etc., etc. So this is not really regulated in the sense that there's a certain operator, but regulated in the sense that there's a maximum output power, maximum, for example, special duty cycles and all these things. What we will also learn is that depending on the frequencies, everyone can operate a radio transmitter. This is true for wireless LAN because they operate in the so-called ISM bands, industrial, scientific, and medical. These are kind of license-free or license-exempt bands. License-free bands, that means you do not need a license to operate your sender in these frequencies. For cellular networks, you need a license. These bands are not license-free. And as we will see when we come to cellular networks, licenses can be very expensive. They can be in the range of billions of euros or dollars. Doesn't matter here. So they can be very expensive. There are certain auctions for licenses, etc., etc. So these are not license-free bands. So you cannot just go ahead and say, okay, tomorrow I will start my own cellular network. This is simply not allowed. So now these are the classical technologies, and I bet you have heard of LTE, long-term evolution, 4G, 5G, whatever systems. So now talking about frequencies, why do operators like LTE? For LTE, we can use the transceivers with really great flexibility. I will come back to LTE, to the technology in later chapters. But here, talking about frequencies, you can already see we can use LTE on many different so-called carrier frequencies. Around these frequencies, we use LTE. LTE, it's split up in different so-called bands, but LTE can be used at 850 megahertz, 900, but also 1700, 2100, whatever. many different frequencies depending on the region where you live, where you operate the device. The frequencies are available or not, and the operators then can use these frequencies or not. We'll also later learn why we sometimes have something like so-called paired bands, so frequency range for an uplink and for a downlink. Uplink, that is always the direction from your mobile phone to the base station, and downlink is from the base station to your mobile or cellular phone. We'll also learn something about what the duplex spacing means, etc., and the available bandwidths of the channel. These channel bandwidths, directly translate into the maximum capacity in bits per second, so the capacity you can use on a certain frequency. So you see, LTE is not limited to a certain frequency, but LTE contains a basic principle of transmission of data, and you can use this on many different frequencies. And today we have the technology that the transceivers can adapt to the carrier frequency and say, okay, in this region I use, for example, 1800 megahertz. But some regions maybe you cannot use 1800 because there's still a GSM system in operation. But more and more the operators replace the second and third generation, so GSM and UMTS systems, with LTE. So that means, let's say 10 years from now, maybe we will not have second and third generation systems anymore. We will only have LTE and whatever there will be LTE advanced systems. Okay, so now we know a bit about frequencies we can use. But what does it mean to use a frequency? Well, first of all, we have to look into signals. What is a signal? Well, by definition, a signal is a physical representation of data. For example, signals you will find everywhere. For example, an audio signal is a physical representation of data. That's maybe music or what I'm talking, my voice, etc. So, physical representation of data. So a signal is also a function of time and location. So at a certain time, at a certain location, you have a certain signal strength. So now, let's keep it very simple. You have a signal represented here. That might be a signal at a certain point in space over time, and that might be the amplitude of the signal. So how strong is the signal? So I'm standing here somewhere in a room, and I simply measure the strength of a signal at a certain frequency, for example. Doesn't matter. Okay? And at a certain point in time, the signal has certain amplitude. So amplitude is one parameter of a signal. I can also measure a frequency of a signal. Well, frequencies, we learned a bit about frequencies. That means, for example, there are carrier frequencies, etc. So if I have a nice sine wave, this should be a sine wave. Okay, I'm not perfect there, but you can imagine what it means. So we have a certain period, because sine wave repeats after a certain period, and 1 divided by period is the frequency. Okay, so signal parameters down here are the amplitude, how strong is the signal, and the frequency. We have some more like the phase shift. I will explain later just to make it complete here. So now what do? Basically, we code our data. We're in computer science, so all we know is zeros and ones. So our zeros and ones, we code this data into the signal parameters. So our zeros and ones directly influence the signal parameters. For example, a 1 could be a large amplitude and a 0, nothing at all, for example. Very simple on-off scheme, for example. Or a 0 could be a low frequency and a 1 could be a high frequency. So 0, 1, 0, 1, for example. So we code data into signal parameters. If you go back to computer networks, we could discuss there continuous time, discrete times, analog signals, digital signals. So usually inside our computers we use digital signals. We have discrete values. Think of voltage, for example, voltage over time on a signal bus. Then the voltage, low voltage, high voltage, low voltage, high voltage, etc. Something like this. So these are digital signals. At discrete points in time, we have a discrete value. Either, let's say, 0.1 volts or up there maybe 5 volts. Something like this. Just an example. Analog signals, well, continuous time, continuous values. That would be, well, this kind of arbitrary signal. So it's continuous. That was the difference. Look it up if you're not familiar with these concepts. So, what do we do now? The basic idea is, before we transmit any data, we have to squeeze this data or map the data onto certain signal parameters. And what can we do? Let's have a look on a very simple signal, a sine wave. A sine wave, nothing but amplitude times sine of, etc. 2 pi ft t plus phi. Phi is our phase shift. I will come back to this. F is our frequency. And A is the amplitude. And the little index t means, well, we can change the values. And the only trick is now, depending on the data we have, we change the values of F, A, and phi. So frequency, amplitude, and phase shift. So a 0, as shown, could be a low amplitude or a low frequency or no phase shift. A 1 could be a high amplitude or a high frequency or a certain phase shift, 90 degrees. What this means in a minute. So that's all we do right now. We map data onto these signal parameters. Okay. But still we are with signals. Well, signals, they have some problems. Before we come to the problems, what is a signal? Well, if you go back to either math, bachelor courses, math, or maybe in physics or our computer network lecture, you might remember, there was something like Fourier representation of periodic signals. I will not go into details. Here, it's important just to know that, think of any periodic signal. Here, it's shown as an ideal periodic signal. Every periodic signal can be represented by a certain sum of sine and cosine with different amplitudes, A and Bn, and frequencies. So you have the F, N times F, I will come back to this. And you have the amplitudes, and maybe you have a DC part, direct current, that only shifts the whole signal. So, why is this important? Real technical systems never ever can transmit ideal signals. This is just something we use for explanation. Even in a perfect computer, this ideal signal would look like, well, something like this, and you go down, well, something like this. So, there is no ideal signal in real systems. What does it mean to have this ideal signal? Or what does Fourier representation of a periodic signal mean? It says basically that you can represent a periodic signal by a composition of so-called harmonics. If you look up the formula up there, you see n times f. So you have a base frequencies and the multiple of these frequencies. These are our harmonics. So, by composition, that means adding different harmonics with different amplitude, you can approach this ideal signal. The more harmonics you take, the closer you come to the ideal signal, as we explained in computer networks. So if you only take a few harmonics, the signal more looks like this. If you take more harmonics, the signal, this ideal signal, would more look like this. That's the idea. What does it mean for us? To really represent an ideal periodic signal, you would need an infinite number of frequencies. So, infinite high frequencies, infinite number of harmonics. That means an infinite number of frequencies. Okay. So, to represent the signal on the left-hand side, this ideal signal, we need an infinite number of frequencies. Okay, infinite and real systems, that's a problem. Okay, but also we need, as you see on the right-hand side, a certain amount of low frequencies. For example, the blue one. The blue one is low, the red one is relatively high. So, low frequencies and high frequencies. Only if you have all the necessary low frequencies and all the high frequencies, you can represent this signal. Now think of your signal you want to transmit, well, your data 1011011010, etc. Well, this might look inside the computer like a ideal periodic or ideal signal. And if you want to transmit this, well, all you need is a good, realistic composition of these harmonics. And now we have a problem. Why? Let's look at real technical systems. Real technical systems are always bandwidth limited. What does it mean? First of all, on the x-axis we have the frequency. So that's our spectrum. Starts with 0 Hertz, so that would be the DC part, direct current part, and goes up to whatever, doesn't matter. So no numbers here, doesn't matter here. On the y-axis we see the attenuation. Strong attenuation, that means we will not receive anything from the signal. Only low attenuation, there's always some attenuation. Low attenuation means, well, the signal is still strong enough on the receiver side. And all technical systems have this kind of bathtub-shaped behavior that for lower frequencies, well, it's difficult to transmit something because you have high attenuation. Think of fiber optics. Take a battery and then try to transmit something like direct current through a fiber. Doesn't work. Even low frequencies, try to transmit, let's say, a analog radio station, 88 megahertz, through fiber optics. Doesn't work. Fiber optics are fiber optics for optical transmission. That means waves with frequencies 300 terahertz and higher. Visible light, for example, or infrared light. And the same is true for all other technical systems. So for low frequencies, so for very low frequencies, they do not really work. So you have high attenuation, so you cannot really use this lower part of our spectrum, because there's a certain threshold. So you need a certain signal strength before you really receive something useful. Let's assume it's somewhere here. The same problem, well, appears with very high frequencies. Well, if you, for example, take a light and then with your smartphone and you shine into your antenna, nothing happens. Or if you have a coax cable and you take a really bright light, nothing happens. Because a coax cable has a certain bandwidth, and light will not go through the coax cable. The frequency is simply too high. So we cannot use the high frequencies here. So all we can use is a certain bandwidth of the spectrum. So this bandwidth is limited by the environment, the antennas, the transmitter, the receiver, a lot of hardware, etc., etc. So a good example is a wall, a concrete wall. Well, again, use the brightest laser pointer and try to squeeze whatever you light through this wall. Doesn't work. But no problem for your wireless LAN. There's some attenuation, okay? The signal is weaker on the other side of the wall, but the radio waves penetrate the wall. Light is also an electromagnetic wave, but it will not penetrate the wall. Okay, interesting. But it works for a window. Just a simple question. Why can you see through a window? Not that simple to explain, but, well, obviously the sun shines through a window, so that means the electromagnetic waves of the sun go through the window. But we can be happy that our atmosphere filters out the ultraviolet light, well, these are higher frequencies, because we really had a lot of problems with skin cancer. So, we see these bandwidth limitations all over in all real systems. Now, back to Fourier. Fourier told us to really represent our nice signal. Let's assume we want to transmit something like this. We need low frequencies, well, higher frequencies, just an example, and really high frequencies. Now, if we map these frequencies onto these bandwidth limitations, we see low frequencies, they would be somewhere here, do not work, really low frequencies. High frequencies, somewhere here, do not work. So, low, they disappear, high, they disappear. What is left are, well, the frequencies in between with different quality. So that means no matter what you want to do with real technical systems, you can never ever transmit these kind of ideal signals. That means all the systems are bandwidth limited. And then if you go back to Shannon, you will see this bandwidth is very prominent in the calculation of the data rate. There was something like signal to noise ratio. Let's ignore this, but here the bandwidth of the system, that's relevant. That directly limits the data rate in bit per second. So that's the Shannon limit. There are post-Shannon systems, etc. I will come back to this later on. So now you know, Fourier, real life, there are some problems. Back to signals. Okay, so signals, physical representation of data. So before we go deeper into signals, first of all, how do we represent signals? We can show the amplitude, we can show frequencies, constellations. What does it mean? If you use, for example, an oscilloscope, You're used to this representation of, you see the signal over time. You see the amplitude of the signal. You can compare signals, for example. So this is very useful if you have, for example, a single frequency and you want to see something, what's going on with this frequency, or you have two signals and you want to compare two sine waves, for example. So this is fine in oscilloscope. But as soon as you have a mixture of different signals with different frequencies, that means you occupy a larger bandwidth, so morphed spectrum. You cannot use the oscilloscope. It's difficult to see some of the effects. What you can use then is a so-called spectrum analyzer. Spectrum analyzers, they display the spectrum. So that means the amplitude of certain frequencies. If you have a single frequency as one sine wave in your oscilloscope, this is a single spike in your spectrum analyzer. If we have more frequencies, you will see more and more, or you will see something like this whole spectrum. So if you look at a certain spectrum, let's say 1 gigahertz to 3 gigahertz, you will see all these added signals of different frequencies. So, a spectrum analyzer operates in the frequency domain and an oscilloscope operates in the time domain. To go from frequency to time domain and vice versa, we can use the Fourier transform. Okay, so spectrum is one way of representing frequencies in the frequency domain. And then you will also see something you might not used to, so-called constellation diagram. This is used to show the amplitude of a signal and the phase. A phase is always relative to another signal. So, for example, you see here as a vector the certain length, and this length is the amplitude of the signal, and the phase is the angle. And this is used for, well, explaining especially and showing how you map bit patterns onto signals. I will come back to this. Okay, so if you look at the phase, on the right-hand side of the constellation diagram, you see this angle. If you look at the time domain, you can directly see a phase shift between two sine waves, phase shift of phi, between this purple sine wave and the black one. So that is a phase shift. You shift the signal. You shift it. Same signal, but shifted in time. And the constellation diagram, this is reflected by the angle. Okay, so, now the problem we have is, inside the computer, we at least assume to have digital signals. We have zeros and ones. They're quite obviously digital, zeros and ones, discrete values. We do not have 0.37, something like this. So these are logical values, zeros and ones. That's our world in computer science. We want to transmit them. We cannot directly transmit them because this would require infinite frequencies for perfect transmission. But maybe we can do a certain trick. And this trick will be also explained in the next section. What we do is we modulate a certain carrier frequency. And then we have analog signals, we can transmit them. Via carrier frequency, how this is done in the next section. Before we can do all this modulation, etc., well, we have to transmit somehow signals. Because right now we know what a signal is, how it might look like, well, this is a signal, okay, nice, but how do we transmit it? And you all know we need transmitters and receivers. Those are typically the hardware, circuits, amplifiers, and all these things. But what is also quite important is an antenna. So we need some kind of antenna to transmit and to receive signals. You can always use an antenna in both directions. So if an antenna can transmit signals, an antenna can also receive signals. So the next step to transmit our data is antennas. Before we have a look into real antennas, first of all, a theoretical antenna, the so-called isotropic radiator. So what does an antenna do? Basically, the antenna radiates electromagnetic waves and receives electromagnetic waves. So you couple wires to space. That's the basic idea. We don't need any medium. That's what people thought more than 100 years ago. But today we know, well, we don't need the medium. We need an antenna, a transmitter, and a receiver. To compare antennas, we first have a look to an ideal antenna, this isotropic radiator. So that is a reference antenna, a theoretical reference, and that's basically only a point in space. And if you send out the electromagnetic wave, no matter how you look on this ideal antenna, in all 3 dimensions, whatever, you see the waves propagating like a balloon. If you just pump air into a balloon, this could be a wavefront just expanding from the center of the ball or balloon. So for this ideal antenna, there is no directive effect. What does it mean? No matter where you measure, the signal strength doesn't matter from which direction. At the same distance, you will have the same energy in the signal. Energy is important because you need a certain amount of energy in a signal to transmit data. Without energy, you cannot transmit data. So we need a certain energy in the signal to transmit data. So the ideal isotropic radiator emits the waves from a center in all directions. So the so-called radiation pattern, well, is this circle or sphere, if you draw it in a 3D. Real antennas are different. They always have directive effects, vertically, horizontally, etc., etc. We will see. Because real antennas, for example, need a power feed, a cable. And the propagation characteristics, at least in the direction of a cable, is not the same compared to the propagation into free open space. So real antennas, they have directive effects. But we can use them. Because this ideal isotropic radiator might be nice to tell something to the universe, but not so good to transmit, for example, cellular data into a crowded street. So, how did it all start many years ago? With very simple antennas. So, I already mentioned in the first chapter Heinrich Hertz, and he used an antenna that looked like this, what is called today the Hertzian dipole. And this is a classical antenna with a certain radiation pattern that more looks like a kind of a donut. If you look from the y-axis to this radiation pattern, that's this donut shape. Because if you look at the wavefront, it looks more like this expanding in these directions. Well, in all the directions. I cannot draw this that good. But that's the radiation pattern of a very simple Hertzian dipole. So it's directed. classical analog antennas for TV, analog TV, or a classical rooftop antenna for cars. Are these antennas mounted on a metal surface? And then you have these small, short antennas you see on the cars. So, what is important? The interesting thing is, if you have these directed antennas, you have a certain gain, antenna gain. That's the maximum power in the direction of the main lobe, compared to the power of an isotropic radiator with the same average power. So that means you pump a certain amount of energy into the antenna, and then you compare your theoretical isotropic radiator with your real system. And then in the direction of the main lobe, you measure the signal strength, the power of the signal. And then you can compare, and this is then your gain you get. Because you can imagine the power you pump into this antenna is not evenly distributed over a sphere like in the isotropic, idealistic radiator, but you unevenly distribute the energy, mainly towards the main lobe. That's the first thing we see. Second, we see, we should not use arbitrary length for antennas, but the shape of the antenna should be proportional to the wavelength. So for this rooftop mounted antennas, lambda fourth is an ideal antenna. For Hertzian dipoles, lambda half is the ideal size. That does not mean that you can only transmit waves of this exact frequency. That only means then the antenna is in ideal resonance and, well, operates in a kind of a perfect way. Sure, you can use a bit lower and higher frequencies, but you cannot use the same antenna for completely different frequencies. That's also one of the reasons your mobile phone of today has many different antennas. You have a GPS system and a Bluetooth system and a wireless LAN and LTE and GSM and UMTS and whatever it is. And they operate on different frequencies, have different characteristics, and this also means, I need different antennas. You can easily use the same antenna, for example, for Bluetooth and wireless LANs, because they operate on the same frequencies. You can also have two different antennas. So, let's just, for the perfect case, use lambda fourth, lambda half, depending on the size of the antenna. You can transmit in a perfect way certain frequencies. You can also adjust this antenna, not by cutting it, but in an electronic way. But that's, again, electrical engineering. We are here in computer science. For us, it's important to see, real antennas, they have this directive effect. Where do we use it? The antennas we use, well, they have their main lobe, for example, down to the street. This is the antenna pole, and then we might have the antenna tilted a bit, and then the main lobe towards the street where all the people are. Why should I send a lot of energy into the sky? Not useful. So the main energy should go down on the street. Or if you have wall-mounted antennas, flat or planar antennas, well, why sending a lot of energy into the wall? No, you want to, transmit most of the energy towards the classroom, for example, towards the students with all their laptops. So that's the idea there. All these antennas, they have also some other lobes here, etc. So, but the main lobe should go towards the street, for example. That's the idea. So, different patterns, and you can not only cover a valley with these different patterns, but you can also build up sectorized antennas. What does it mean? So, for example, if you look at these huge antennas or antennas on buildings, you quite often see not only one, but many antennas. And this means that each of the antenna is responsible for a certain area. A 3-sector, for example, each antenna is responsible for 120 degrees, 6-sector, etc., to cover a larger region. Why do we do this compared to a so-called omnidirectional antenna? Because we can have a way higher capacity this way, because within the range of one antenna we can have a certain capacity of mobile phone users or data rate, etc. And if we sectorize the region, then we can have altogether a higher capacity compared to a single omnidirectional antenna. Okay, I will come back to frequencies and how to reuse frequencies later in this chapter. Okay, so our antennas can be directed and sectorized. What else? We can use more than one antenna. We can group antennas. What does it mean? So for example, on our car, roof of the car, we can have 2 or more antennas, or we can have a whole antenna array. Why should we do this? Well, for example, if you have a base station somewhere with an antenna, and then you send out a radio wave. This will reach all these antennas in this example. But depending on the angle between the base station and your antenna array, the different paths of the signals have different lengths. So the shortest one in this example is number 1, then 2, then 3. What does it mean? If you send out a signal, a peak, so let's assume you send out this beep, a short peak of the signal, then first antenna number 1 will see this peak, then antenna number 2, and then antenna number 3. And now the clever part comes. You can combine these 3 signals in a constructive way. That means you delay for a certain delta the first signal. You also delay the second one, and you do not delay the third one, and then you add them. That means you take the 3 peaks, you bring them together in a constructive way. That means you have to delay them a bit. You delay the signal you reserve first, etc., etc. And then you combine it. And this results in a much, much better signal quality. That's one way of doing it, and this is called diversity combining. So you combine the signals, and this shifting of the signals depending on the path length is called co-phasing. So you bring the phases together to avoid cancellation. You cannot simply add them because they could cancel out each other. Stupid idea. So you need this co-phasing. That means you have to know the time difference. But there's different ways of how you can measure this. I will come back to this as well. So, diversity combining. Alternatively, you can measure the signal strength in each of these 3 antennas, and you only take the antenna with the stronger signal. That's called switched or selection diversity. So for example, it could be the case that there's a huge building in this width and there might be a car here in between. So then we say only number 2 is the winner. And we do not use the signals from antenna 1 and 3. The same can be done with lambda 4th antenna, etc., etc. So you can build up an antenna array. Yes, it's more expensive, but then you can do this diversity combining or switch diversity. You can think of hundreds of these antennas. So antenna diversity is a very important concept. Okay, so if you understood this idea of antenna diversity, diversity combining, you will also understand the next slide. Because what all the systems of today do is they use these multiple antennas, and then we are at MIMO, multiple input, multiple output. So we use several antennas. How is this done and what can we do with it? So your mobile phone of today has several antennas for the same frequency band, same technology. Why? Well, before I explain it, you can increase data rates. Yeah, that's exactly what we want. You can increase transmission range without additional power. You have higher spectral efficiency. That means you can squeeze more bits per second per hertz of your spectrum. It's more robust links and reduced fading, etc. And there are many, many examples. The Wi-Fi standard, .11n, LTE, etc. So what do we do? The interesting part is now sender and receiver both have multiple antennas, multiple input, multiple output. So for sending and receiving. And what you can do now is you can do, if you want, exactly the other way around from our antenna diversity, where we combine it. You can transmit signals with a certain delay. So the sending time, for example, for one component, component 1, from this certain antenna, the closest one, let's say, the closest one to your antenna, we assume now multiple antennas on the sender side and just a single one now on the receiver side, because there are MISO, multiple input, MISO, SISO, etc. systems, so with single input, single output, single antennas, multiple antennas, etc. Here, 3 antennas for the sender, just for the example, 1 antenna on the receiver side. What we do now is, on the sender side, with the antenna closest to you, we send at a certain time t0. Antenna number 2, it's a bit further away from you. We send a bit earlier. By the time D2, earlier. And for antenna 3, which is even further away from you, we're talking here about centimeters, we send even a bit earlier. What is the result? On the receiver side, all the signals will be there at the same time, synchronized, same phase, not at another position. So let's assume you have only one receiver antenna, that's you, and there are some other people, they also want to receive something. You will get the perfect signal as a combination of the 3 signals. But think of the others. For the others, it simply does not fit. Here, the signals are not co-phased, so they might cancel out each other. So, low signal quality. If you do it in a good way, you can form a beam and you can follow a person or an aircraft in the sky by this antenna array. Beamforming. That also means, for example, you can multiplex in space. So you can split your signal with a certain high data rate, signal representing a high data rate, into many lower rate streams, transmitting over different antennas. You can also do something called diversity coding. So you transmit a single data stream, but over different antennas using so-called orthogonal codes. What this means, I will explain later when I come to code division multiplexing. But the interesting part here is, and this is what you can understand right now already, is this beam forming. Beam forming, basically, that's the reverse side of what I explained on the slide before, that you have to co-phase the incoming signals using your different antennas. Now you can actively form a beam and you can follow someone, which is a nice idea. So you can follow different people and there will be almost no interference for the others. Because if you adapt the delay just for one person, for one antenna, then this will be the ideal point in space where you receive the signals. Okay, so that was a lot about frequencies, antennas, and signals, etc. But you have to have a basic understanding of all of this, because otherwise you might think of, what is special about wireless transmission? I know how data is transmitted using fiber optics, so what is the big difference? Yeah, there are some differences. So please do look up how this frequency regulation works in different regions. So there are some pointers here. And then just think of, low frequencies. Cool, they even follow the Earth's surface. That's cool. Look up why. And why don't we use it in computer networks? Low frequencies. Because with low frequencies, perfect, we could penetrate all buildings. So a single wireless LAN hotspot could cover the whole campus of a university. Great. Why don't we do it? So, but then also, why does, for example, the ITUR only regulate lower frequencies? Well, lower, up to some 100 gigahertz, not the real high frequencies. Why does no one really regulate the 350 terahertz range, for example? Think of that. What does it mean? Why? Then I explained a bit the two different approaches in regulation when it comes to Europe, for example, and the US. What are the consequences? What are the pros? What are the cons of these two different approaches? Then think again, why should we have the same ISM band worldwide? Think again of, what about real, ideal digital signals, square waves, as we have them inside a computer? Can we transmit it? What is the problem? So then I showed you directional antennas. So all the real antennas are directional, but is a perfect directional antenna or a really good directional antenna useful for mobile phones? Or rather a kind of an omnidirectional antenna? They all have some directive effects, but what type of antenna might be ideal? How can you improve the gain of an antenna? How can you do this? And if Shannon, Nyquist, etc. is really something, what's that? Please go back to Computer Networks lecture or any other books or Wikipedia or else and refresh your knowledge about this.